So let's think about what kind of algorithm is adapted to 1970s computing power. Now we first need to imagine what is 1970s computing power. Take this. This is what we all, pretty much all of us, in one form or another, have a smartphone, or we have seen smartphones. These smartphones are so ubiquitous that we no longer think on what they are capable of. Imagine this, you have the camera here. The camera has face recognition. It tells you when you take a picture where's the face of the person. It can recognize faces. I sometimes play with it chess. 25 years ago, I used to beat almost any of the computers that play chess that were with reasonable pricing available. This thing, I have to put it to a very low level, then I can still beat it. It's very powerful. By 1970 standard, this is a supercomputer. We've had to deal with the situation in the 1970s that the computing power was much more limited. Memory was limited. I remember my first computer had a hard disk of 8 megabytes. Think about that. Now today's we would have it in terabytes. So this is a supercomputer by 1970 standard. We're looking for an algorithm that a computer at the time could reasonably handle. So question here to you is, what mathematical operations, or what are the operations that a computer does fast? Think about this for a moment. Which operation is the fastest in a computer? Did you guess it? Do you have some ideas? Well, let's discuss this. The simplest, fastest operation that you can do in a computer is writing to memory. The second fastest operation is addition. So, if we can come up with an algorithm that writes to memory and adds numbers, then we're using the fastest operations that our computer can provide in 1970. And this is actually the underlying principle of the back reconstruction principle. What we are doing with back projection, and we'll just take here an example. Let's say we've collected a projection in this direction at 1 pixel, and we've had recorded in the computer a beam intensity of 1, or a detection of 1. So now we write into memory. We'll write along this direction into the memory, we'll write 1s. Now we'll record a next projection orientation, let's say it's here. We'll again, in this direction that we've take the intensity of recorded here, we'll write 1s in this direction, and where we have non-zeros, we'll add. So we'll start out with zeros, we'll write 1s in here, and now we'll add the next intensity on here. This is 1, so here where they intersect, we will have 2. You can do this example, of course, also with 1 and 3, then you would have 4 here, and 3s here. So it's the same principle. So we sum the values in overlapping pixels, and the rest we write in there. And that is for 2 orientations here. We do this for multiple orientations. We can just take any orientation in x prime, y prime, and this is just showing here the function, the projection here. What we're looking at here is just a rotation of the coordinate system that we have with the angle theta. That's what we had in the sinogram. So we're rotating the angles here. So we'll just rotate, we'll do this, we'll rotate, we'll do that. Now, instead of going through the mathematical elaborative way of working out the maths here, I want to illustrate what's happening with gray shades for a point-like object. Let's look at 2 projections. We have 2 projections, so we have taken the computer, we filled in the numbers with this projection, we filled in numbers with this projection, the rest is 0, so here where we overlap we have added. So this gets a bit darker. Let's take 4 projections. When we have 4 projections, 1, 2, 3, 4, again we take the same intensity because it's a pointwise object, and we're starting to add the numbers together here where they overlap, so it gets progressively darker, the grayscale. Now we'll look at 8 projections. This is what we are getting with 8 projections. The overlap here, it's getting darker and darker. Here we still have the same intensity as here. And now with 16 projections, we are starting to see that we have an object here. This is where the original object was. We can start to see that there was some intensity there. So this is with 16 projections. If we look at the reconstruction in real time, this is an example here from a standard phantom. The first 60 projections, the next 60 projections, and so forth. And here there's 180 projections here. The reconstruction is complete. We can see here this so-called Shep-Logan phantom quite nicely. Now, one thing that we have a problem here is we said we had a point light object. So if we have a point light object, if we sum together, we should in the end have a point light object reconstructed. But as we can see here, this gets very blurry with the number of projections. And this is a problem I want to address in the next few minutes. So, why does simple back projection, the algorithm that we have just discussed, have poor spatial resolution? We take with many back projections a pointwise object, we are getting an intensity that looks like this. And we can actually show that the reconstruction of this point object falls off with 1 over r. So instead of a point object, we're getting an object whose intensity falls off with 1 over r. And the question is why? Why is this so? So we'll take the situation here and we'll look at this. Now I'm bringing here an intuitive argument. There's a mathematical proof of this principle. We can show this mathematically. You have this in the exercises. Here we're going to look at the analogy of the light intensity. So when we look at a candle from very close, the candle is bright. If we're looking at it from very distance, the candle is weak. We can barely see that candle. And this analogy I want to use here. So we're going to look at the coordinates in cylindrical coordinates here. We have rho, we have d rho here, we have a d phi, an opening of the angle, and so this dimension here is rho d phi. So this is giving us the area of our voxel here at this point. The area of the voxel is dx dy, that's the infinitesimal area dA. That's rho sine d phi d rho, or this is rho d phi times d rho, that's this times this. That's our voxel size here. So now we can take this, so we're taking this approach here, and we'll see the reconstruction. We have lights, we produce a projection, we have the incident X-rays, this gives us the projection here. For the reconstruction we do the inverse, we do shine light here again, so we have the second projection here, so we've collected these two projections. So to recap, X-rays come in, we collect a projection with this orientation, X-rays come with this direction, we do a projection, collect the projection here, we have the intensity. And now for the reconstruction, what we are doing is the opposite. We're writing the intensity that we saw here into the image. So we are back projecting the light, if you will. We're doing the inverse operation in this direction here. This is the other direction, and we're adding this together. So for the image reconstruction, for the measurement, X-rays come in, this gives us a projection. X-rays come in, this gives us a projection. And then in the computer, we do the reverse. We emit the X-rays in the computer, so to speak, in the direction of this orientation. We fill it in, and we do it here for this angle here. So we're sort of reverting the process. It's like we are shining back to our original object, the intensity with which we have seen the object. So what we are having now is we have a certain angle d phi. We have the area here, which is proportional to rho, to the distance that we are from the pointwise object. Now we've said here in this process that reconstructing with back projection is like we are inverting the process of emitting light. So we have, instead of a candle shining out light in distance, we are shining a light back onto our object. So we're shining this light the X-rays, that's also light, according to the angle back in here. So if we have a certain number of photons counted here, certain intensity, for a given d phi, this intensity is the same, but the area is proportional to rho. So our pixel size, in the end we reconstruct the image with constant pixel size. Our pixel size, the number of back projected intensities for a given pixel size, is constant with d phi, but we want to keep the pixel size constant, dA, and since dA is proportional to rho, then the number of rays that go through it decrease with 1 over rho. And that's the reason behind the fact that a pointwise object is not reconstructed into a pointwise object with simple back projection, but into an object whose intensity falls off with 1 over r. So now the question comes, how can we maintain good image resolution? So with simple back projection, to recap, with simple back projection, our point object becomes something that falls off relatively slowly. The trick here is to use filtered back projection, and the filtering that is done here is a mathematical operation. We'll take our object, here it's supposed to be a pointwise object, the projection that we've measured here. We'll convolute it with a function that has negative wings on the side, and we're getting this projection. And then this is being back projected to form the final image. So what does this do? We have said a point object produces, in the reconstruction, produces wings that fall off with r over r. We want the point object to be represented by a point object. So what we're doing is we're convoluting the measured projection with the function that has negative wings on the sides. That's this convolution operation here, and we're getting this kind of projection. So now let's think about here, what are the consequences for the image? Are there any consequences for sensitivity? How about resolution? Well, resolution, if with this we are getting back our pointwise object, the resolution improves. We're getting from a point object to a point object, so that's good. What about sensitivity? Remember, back projection is a process where we add numbers. Now our projection here has negative tails on the sides, so this reduces the number of additions that we do in a computer, so it reduces the sensitivity. So we're back to the old game in biomedical imaging. On one side we have sensitivity, on the other side we have resolution, and the two things are fighting against each other. So we are going to lose some sensitivity. So here's a original sinogram of an object. We just have a pointwise object. Here's the sinogram. Then we do the back projections. So in white are the negative intensities. This is 1, 2, 8, 32, and 64. And here we're getting very nicely from the back projections, we're getting a nice definition of our original object. Here's another filtered back projection example. For a larger object, we have 2 projections, 4 projections, 8 projections, and so on. With 64 projects, we get the nice square phantom. If we don't do filtered back projections, this is this example here, this is what we would be getting. So we are getting a blurry image. This is definitely not something that we would want. To give you an example of a real-life image, this is a back projected image of the abdomen, the thorax. We can start to see some organs in there, but it is really very blurry. Now think what you're going to see next. It's the same image, but now reconstructed with filtered back projection. And here it is, same image. We get a much clearer depiction of the internal structure, much better resolution, even though we've sacrificed sensitivity. This image here has a lot of intensity. We've sacrificed it to gain resolution and the anatomical detail. So in this video, as it loops through, you're seeing the reconstruction of the image through the process of back projection. At the beginning, we can hardly see what the object is, and as it reconstructs, we're seeing that it reconstructs into 4 different vials of different absorption that are depicted. So we can see the process here as it loops through of the reconstruction or filtered back projection reconstruction. I'll show it here in individual slices. So this is now an in vivo example from the heart. As we start out with one projection, multiple projections, increase the number of projections, we can still see not much. Now we're starting to guess that there is something in the center, but still we cannot detect much of a structure. And as we come to the end, we are seeing here the reconstruction. This is actually a specific scan of the heart. Now we'll take these 8 images, and here in this looping animation we're seeing the same 8 images, the process of reconstruction, so we can visualize this process in the computer as we are continuously back projecting, how this summation of the intensities produces a picture here of an anatomical organ. And here we have the looping presentation of the vials filled with different substances. X-ray techniques, what we've seen is, once we see a radon transform, we can reconstruct the image using back projection. And this is essentially a technique that's being used for all the X-ray techniques. It's the fundamental technique. Yet, we are also going to talk about MRI, and there the major technique that's being used is Fourier transformation. And there is indeed a link between the two, and this is what I want to discuss here briefly. We have the reconstruction of an image, so we have the image space and the final image. In CT, this is the acquired data. So this is the image space. Then in terms of Fourier language, we have the Fourier space or K-space or inverse space, or there are other terminologies. In MRI, it's used K-space. This is the acquired data in MRI, so this is the Fourier transform of the object, the Fourier space. That's what's being acquired. In CT, we're directly acquiring the image. Now let's take the linear attenuation coefficient. We'll do a Fourier transformation. And if we do a two-dimensional Fourier transformation, so we're doing the Fourier transformation of an object that's represented in real space, that's what we know. We get into the Fourier space or K-space, and there the object is represented by the coordinates kx and ky instead of x and y. Here's the Fourier transformation. We have just disregarded the normalization constants at the beginning. So, to illustrate the principle here. So this is, we can take the linear attenuation coefficient, Fourier transform it, and we get a representation of the object. This at the EPFL is dealt with for the students with the course Signals and Systems. Now, if we do the inverse Fourier transformation of this data, then we obviously come back to the linear attenuation coefficient of the object. Now, let's say we have our object in Fourier space, K-space, and while we'll set the K-space coordinate along x to 0. Then we have this expression here, so m0 along ky is this term here. Can you recognize what this is? Well, this is, if we look at this here very clearly, this is a projection. This is the radon transform of mu. So this is the projection of mu onto y. So this, what we are looking at here, is the Fourier transformation. If we do the Fourier transformation of the radon transform, we're getting one line in K-space. And this is the central slice theorem. Central because Kx is 0. So, in principle, we can relate the data that we obtain with radon transform to something that we have acquired in K-space or Fourier space, and then we could, in theory, do Fourier transformation. And this, in theory, can be done. This, however, in practice leads to artifacts. This is the Shep-Logan phantom, and here we see ringing artifacts. And the question is to reconstruct this better using Fourier transformation, but back projection is still a dominant method of image reconstruction for X-ray based techniques. There are also iterative algorithms that are being used. But the point here is we will be talking about reconstruction of images using MRI, and that there is a link between CT and MRI reconstruction.